Recording in progress.
All right, so we are now recording. Yeah, all right, great. So let's go ahead and let's start with the whiteboard. So I'll just do a quick summary. So today I think is a pretty important lecture, if you will. All right, so the topic is transformers, right? So we're covering transformers. I gave you that, we'll go to the book today, but I gave you the copy of my book, right? And you can just read that chapter 10 on transformers. Remember that chapter 10 is the first transformer, which is called the encoder decoder with multi-head attention. Okay, that's the very first one. The architecture looks like this, right? Inputs go here. The encoded output goes here. You have another input, the second input that goes here. Your predictions go here. This is the encoder part. This is the decoder. This is the 2017 paper by Vaswani et al. Okay, that's the original. That's what I gave you in the book. Since then, there have been many variations of this idea, as you have seen, including BERT and all the BERT variants like Roberta. So if you see Robert, right? And so that's the whole family, all the BERT ones. And then there's the ones that are BART and GPT, which are a different family. But they're all transformers one way or another. To be a transformer, you use the attention mechanism. So we talked about attention. You can refer back to one of the lectures for that one, the keys, values, and everything. And you use one of these ideas of encoder or decoder or both. So the original uses an encoder and a decoder. BERT only uses encoder. BART GPT use encoder and decoder, okay, in the architecture. So that's the first thing to remember, to kind of place us where we need to be, okay? Any questions about this part or no? Okay. Now, most of transformers, I'm recording this. Most transformers were done initially for NLP, right? Which is, usually text. But they're being used now, believe it or not, for vision. And there's a battle raging right now between CNNs and the transformer for vision. I don't know the exact name of it yet. And it could be that they win. So you'll see CNNs not being used that much anymore. That's a possibility. So we'll see. But we're not going to spend too much time on this semester. If anything, I'll do a lecture at the end. Okay. But our focus is here. So notice I started with transformers, what they are. Chapter 10 in the book, encoder decoder, several variants. They need to have an attention mechanism and one of these elements, usually to be called a transformer. Then we set the transformers, actually NLP and vision. Our focus is on NLP. Okay. All right, then we say, so now we are in the transformers NLP approach. Okay, and here, last week, we started talking about applications. Applications in general, but it's a good classification of applications would probably be the standard application of supervised. Well, no, let me not say that. So I want to stress something important here. In the transformers have two phases. What are they? What are the two phases of transformers? Guys? Pre-training. So if pre-training is one phase, what is the second phase? Fine
tuning.
Fine tuning, right? Okay. Pre-training is done on, let's say for instance, let's take a statistic. You guys probably know this better than me because you know a lot more about computers, but if you think, would you say 2.5 terabytes is a lot of data? Of text data? Imagine, I don't mean movies, I just mean like text.
So much.
So much, right? A common crawl, how many terabytes do your GPU boxes have? I think mine has 2 terabytes and this is 2.5, right? So it doesn't even fit on my hard drive. So think about it, 2.5 terabytes of a common crawl. A common crawl is the term given to a crawler that scrapes the web, right? Common crawl for a specific set of text. So for instance, one of the transformers, Roberta, I think Roberta, is it XLM? I'm not sure. One of these versions, which is a BERT transformer, was trained on 2.5 terabytes of data. That data is usually what? Not labeled, correct? Instead, the transformer learns in an unsupervised fashion. But that's the, what do you call it? The pre-training phase. So for instance, if we think of the transformer as this, and we want to predict the cat sleeps, and that's the first sentence. And then we want to predict the next sentence, which would be, and then it wakes up, then this input would go here, the next sentence, and then wakes, right, would go here. What the transformer should predict is, and then wakes up. So up is the word that should be predicted. Does this make sense? Guys?
Yeah.
Yeah. So what I'm saying is, why is this unsupervised? Because you have 2.5 terabytes of text where you have sentences followed by what? Other sentences, right? So every 2 sentences, you grab a sentence, you just grab the next. You have what is called the next sentence prediction problem, where we have the cat sleeps and then the next sentence and then wakes up. The car is going fast and the pedestrians got out of the way. Do you guys see why it's unsupervised? That's really the only thing you need to understand here. That pre-training can be done like this. Now, this is not exactly how it's done, but it's a simple explanation just to give you the intuition of why it's, in particular, why I want to say that it is unsupervised here. Any questions about that? Okay, I'm not hearing any questions. So then phase two, you pre-train this model on 2.5 terabytes of come and crawl or whatever of text, and you're just predicting next sentence. However, there are other things that you can predict in an unsupervised fashion. The intuition is that it learns, you know, structure of grammar, it actually learns semantics, etc., from the 2.5. And now that model is ready. It's basically a gigantic machine of codifying things. Okay. And then once I have the phase one complete, comes the fine tuning, right? Which is for your specific problem, we are going to fine tune it to the task. So we're going to fine tune it to the task. Sorry. Oops. We're going to fine tune it to the task here. So what are some approaches? So this is what so we're actually back where we were last Monday, where I was saying the applications of NLP. But before I say that, how can we fine tune it? Well, we can fine tune it here in a supervised fashion and also in an unsupervised fashion, okay? Supervised and unsupervised. So last week then, so now I'm gonna jump to just a fine tuning part, although today I'll talk more about phase one as it pertains to BERT. We're actually gonna come back to like this idea here. But let me just finish this story, let's say, of phase two, the fine tuning. So let's go to another slide. So now we are in fine tuning of transformers. And then we have supervised and we have unsupervised. So we haven't talked about unsupervised at all, but I have the code for that today. All right, and that code, the unsupervised, actually, I'm not even using my GPU box. It just runs nicely on the Windows computer. All right, but supervised, let's kind of summarize here. What are the two, let's see if you guys remember, what were the two classes of supervised applications we talked about last week? You remember? Two modules from transformers. So we had modules. Yeah, go ahead.
Was it the sequence one?
Yes, that's one. Very good. What's the other one?
I'm trying to remember.
The token one, but yeah, good.
Oh.
So the name is really weird. Like I would have just said for label classification, right? But the word that they use is for sequence classification, which I guess the sequence just means the input. Right? But really this just predicts labels. So this is, this example is like that Turkish one, right? So the Turkish one where we actually had labels. Oops. Label and text, right? And so we train on this. So this was the Turkish one. If I go, I want to remind you of that one. So we can, let me share this screen. Okay, and here you should be seeing the GitHub. And then we go to repositories, transfer learning, target phase, and then fine tuning. And these are the ones that we looked at, not all of them, but in particular, we looked at one of these, I think. Was it this one? No, this is the sentence classification. Yeah, this one. So this was the data set. Remember, these were the Turkish labels. We can look at the data set itself. Some data. And you can see we had it here where we have, this is one sample. There are no commas except for the comma that separates. This is the category from the text itself. So you're going to fine tune, given some text, to predict the label, where all of this text needs to run through a transformer for the encoding, basically. All right, so this is the supervised approach. And if we go back, fine tuning, there were several examples, but mainly some of them were like sentiment classification. This one was multi-class, and then we had some regression ones. But really, what I'm going to do today is I think it's better. So in essence, that's the idea, right? So we did that one. And in this case, these for sequence classifications, actually, let me get that right. So if I look at this, yeah, here it is. So for sequence classification, so I had it right. So it usually starts with whatever model you're using, like BERT or something, but it's for sequence classification. So let's go back to the whiteboard. So that's, let's say, one type of approach, right? That's one type of approach. Number one, for sequence classification, the output is for any amount of text, one label. The second one was the other type for token classification. I have not given you code for this one. But what this one does is, instead of given text and producing one label, you produce a sequence of labels for a sequence of text. So for instance, this is applied for part of speech tagging and also for named entity recognition. So what I mean by that is, if I go to another page here, let's take the example of named entity recognition. You know, the input is the princess Mary entered the dark woods of Engar. Some example like that from the literature. So this is the input. If this was for sequence classification, it would just give us a whole label. Like for instance, this might say scary, right? You know, if it was something like that. But for token classification, which I believe that was the module? Do you guys remember? It should be, yeah, for token classification, that's definitely the name. Then it's gonna predict. So tell me, of these words, which ones are entities?
Mary.
Mary is a person, right? What about the dark woods of Engar?
That's a little more questionable. Is it going to see the capital and then just assume darkened woods
It's
are?
not by. Don't assume just by capital. Assume it's like you. It's smart. Is that an entity?
Well, if it's smart, then yes, it would assume so.
What would be the dark woods of Engar? What type of an entity?
I mean, it's a place.
It's a place, right? Like if I say I'm going to New York City is an entity, right? So in this case, let's say location. Does this make sense?
Mhm.
And what about princess?
Yeah, person.
It's a type of person, right? Exactly. Very good. So remember, with transformers, no, don't just like assume. You need to assume more. You know, that's kind of the insight here. You need to start assuming a little bit more about where you are, believe it or not, in AI, right? So there's a little bit more intelligence going on there. Now, what about the? That's not an entity, correct? So we say it's an O. Entered, is that an entity?
No.
Nope.
Great. All right, so then for token classification, hopefully it's clear that the output is this: a sequence of tokens given an input. Okay. And so this applies very well for the problem. So now if we go back for big picture, remember, for pre-training, it's unsupervised. For fine tuning, it can be supervised and unsupervised. Last week, we talked about supervised. So this one for sequence classification, and I gave you the Turkish code. I didn't do anything on this one, but part of speech tagging, named entity recognition, question and answering, these are all for token classification. And we may not do this in class, but the code is out there online. And so this gives you, this part of speech tagging is, of course, the cat sleeps or eats. So determiner, what is this one? It's a noun, correct? Or no? Verb, and so on. Same thing, right? You get this sequence, you get that as an input, and you get this sequence as an output. But these are still, would you agree that these are still supervised? That means that you need to have labeled data, right? In the case of, for token classification, you're going to need examples that look like this, or examples that look like this, and then do the prediction. Is this clear enough?
Mhm.
All right. All right, so this is kind of where we were last week. Now, today, we're going to look at the unsupervised during the second half of the class. So this lecture will go on until start at 2:30, 3:50, right? So yeah, so I'm just doing this part, and then the rest of today, and the rest of the first half, I'll cover BERT, and then in the second half, I will cover this one. But I wanted to point where we are, right? So in unsupervised, obviously, as the name implies, there's no labeled data. So all you can do is clustering, semantic analysis, or distance metrics. So for instance, let's take the Turkish example, right? Let's go back to that Turkish example. So in that one, I had a label and some text. And let's say it's label 1, text 1. And then I had label 2, text 2. You guys see that? So this is the supervised case. I train it with these. In this scenario, unsupervised, I no longer have the labels. I just have the text. So what can I do? Well, you can cluster it. You can do distance metrics. If you remember, where do you do those things? What is this called? With multiple dimensions? What do we call this?
Vector space.
Vector space. Very good. Thank you. We need to operate in vector spaces. If we can operate in vector spaces, that means that we're going to represent the text as vectors of dimension n, where we don't want it to be too big. So n can be something like 768. Why not? Not so big, right? And so we're going to represent all of these I chose 768 because I believe that is BERT's dimension. We'll see that in a second. So now text 1, text 2, text 3 can be points in this space, correct? Would you agree with that?
Yep.
And then what can we do? I can cluster them, I can take distance metrics and so on. You see that? So that's basically how that works. So this is where we are. So on the fine tuning, so I'll show today examples of this. So if we were talking now, going back to that idea of the project, remember what I said, I have some text and then I have other text, but this text has a label, right? I want to infer that this text should get that label. So what can I do? If I use unsupervised methods, I represent this as a vector of 768, and I represent this one as a vector of 768. Take the distance between the two vectors, and then in all the other vectors, find the closest ones, and then for the closest ones, find a label. Does that algorithm sound familiar to you? What was the name of that algorithm that you learned in 360?
Nearest neighbors.
Hey, nearest neighbor. Very good. Do you see what I'm, oops, I don't know what happened there. You see what I'm doing here? So I'm saying that somehow we're going to use a pre-trained transformer, but on the fine tuning part, instead of kind of like training it, so we're not fine tuning it in a way, right? Instead, I'm just saying we're using the pre-train. So a better way of saying this is that we have phase 1 pre-trained model. We have phase 2 where we can fine-tune supervised ones, and unsupervised ones maybe just means that we use pre-train. There is maybe no element of fine-tuning, but it is just the second phase. That's why the better term was second phase over, let's say, fine-tuning. Is this concept clear enough, guys? Any questions? Okay, doesn't sound like there's any questions. So anyway, this is what we're doing today. And so maybe this makes a little bit more sense as to what I was saying last week, right? That we need to find a problem and do some inference somehow. Okay. All right. So anyway, you have a lot of tools. You'll have more tools now, right? So that was, I think, it. So let me just summarize it. So as far as NLP applications with transformers, you guys can now, or should be able to, hopefully at least after today, you can do several things. Sequence classification. Sequence classification, so that means, you know, you have a label and text, like the Turkish example. And basically that's what you do. So there's your sentiment analysis or any other classification, topic classification. For the token classification, they're also this kind of the same thing, supervised, but here you have the cat eats. You predict a sequence such as the part of speech tags, determiner, noun, verb. Or it can be named entity recognition, question and answering, etc. Now today I'm throwing at you unsupervised, where we're not gonna train it on the fine tuning, but we're gonna use the transformer to encode our text. We're gonna encode our text And then we're going to perform some distance metrics. So basically this idea, right? We're going to encode our, so I guess I'm going to draw this. And then now we have our text in here. And this is unsupervised, right? And then one last one that you guys are working on is GPT. What does GPT do? Natural language understanding, basically generate text automatically. And as a side effect of the pre-training, so it's a side effect of the pre-training of, phase 1, right? As a side effect of the pre-training of phase 1 of a transformer with BERT, for instance, what else can we do? So I guess a third category here is masked token generation, right? You remember that because you use that in the homework, the ethics homework. Does this make sense?
Yeah.
Any questions about any of this? No questions? All right. So these are all the applications of transformers. And there you have it. So if I give you now a problem with text processing, you can throw all of these or any of these at it. Okay. And so one of the objectives of the project is I want you to do exactly that. Throw all of these or any one of these at the problem. You currently have code for this one. You will hope have code for this one today. You are working on this code yourself, and you already have these because these were from your ethics homework. The only one that we don't have code for right now that I've given you, obviously there is online, is this one, but it's pretty straightforward. I mean, you can use the pipeline very much like this. At some point, if time permits, I will come back to this. It's just not such a priority for me, but we'll come back to it, okay? But it should be as easy as one of these Albert ones in using the pipeline and just say for that type of problem. All right, so this is what you can do with transformers, okay? So this is the big picture that I wanted to discuss today. Before we move on to the two other topics that I want to discuss today, which are to go over the code for these, but also, if you remember, a week ago or so, I went over the 2017 paper, the original one, and I explained that. Today, I want to go over the, in phase 1, I want to go over BERT and how that works. So, so before I move on, questions or on anything that I just said? No questions. You guys are still there, right? All right.
Yeah.
All right, so there are no questions then. So that hopefully made sense. All right, so then today, in what we have left, should be like half an hour. I should be able to do this. So I'm going to go over BERT in particular. During the second half of class today, we'll go over the code for the unsupervised methods, the similarity, distance metrics basically. And then hopefully I'll have 10 minutes or so at the end, remind me, so that we can once again talk about the project and see if it's a little bit clearer now for your objectives. Okay, sound good? All right, so let's start then with the second half of the lecture, which is BERT. So actually for this, let's go back to the calendar. So I'm sharing the calendar here. Nope. All right, so if we go to the course, you'll see that today I've called this, it's really for the name. I have called this a lecture today, word embeddings, encodings, and their connection to BERT. So it's actually pretty interesting because the story of BERT, although it's a story of transformers, it's better understood in the context of word embeddings. So like the classical word tovec, all right, and encoders, etc. BERT, in a sense, is just a big embedding machine. Okay, so it's a big embedding machine which uses the ideas of the transformer, in particular, the encoder and the attention mechanism that we described last week. And then the second half of it would be, of course, transformers for semantic text similarity, which is the unsupervised after phase 2 or fine tuning, if you want to call it that. And then this is what we covered last week, fine tuning for text classification with your own data. And then here, you know, sequence and token classification. So that's basically where we are. All right, so for this, I'm going to open up so basically, I'm going to switch over to the whiteboard again. And now we can formally start the BERT discussion. So actually, we have word embeddings, word embeddings. We have auto-encoders, and then we have BERT. And there's a very strong relationship in the goal. They're all neural networks, obviously. So they're all based on that, but there's a very strong connection there in terms of objectives. So what are word embeddings, first of all? When you guys took 365 or 520, I gave you a problem of clustering some text, right? And you use singular value decomposition, etc. To represent the sentence, you use what technique? What was the name of that technique? To represent any sentence, a sentence or a paragraph as a vector.
Word to vec?
You didn't use word to vector, right?
Oh, bag of words?
Bag of words, very good. Because the story starts with the bag of words. So in the bag of words, we create vectors where the size of the vector is the size of the vocabulary. Do you remember that? Problem is,
Sparse.
It's a sparse matrix. You have 50,000 words in the vocabulary. This is really big. It's very sparse. So what that means is tons of zeros, and then maybe a 1 hidden in there, ... 0, 0. Do you see that? This was a problem. But this was the solution for the longest time. Then came word embeddings, which, as you said, was word to vec. So came word embeddings. And in particular, word to vec, but others as well, fast text, etc. You know, many others, right? So came word to vec. So whereas before, the problem had been that we have a sentence and we would encode it with a really large vector, which was very sparse. Right? This is really large, right? So let's say 50,000 or something. So that was a problem. So this is bag of words, bow, And instead, we say, you know what? I'm going to use word to vec. These are called distributed vector representations. What's the advantage of it? The dimensionality of the vector is now limited, let's say to 256 features instead of 50,000. So you can see how that's good. It's also not sparse like this. Instead, all the values here, the 256 features, have values in it. They have values. And also, these are features, basically. And each one of these has semantic meaning. So it's no longer sparse, and the features have meaning. What the meaning is, you don't know. You don't predefine. You just say, I want 256. You let the algorithm figure, there's obviously in word to vec, there is an algorithm and an objective function, which basically means what is it that you're trying to optimize, right? So there's an optimization involved. Okay, so you optimize the model, and then it's going to learn. So what I want you to understand is the importance, right? From sparse to this, you got more meaning. It's smaller. You also, you do a lot of things, right? That's really important. Now, this assumes that for every text, the words, maybe I didn't say this, that the words are the ones that are being represented like these vectors, right? So this is the word cat for whatever reason, and that's it, right? And word to vec here does the same thing. It's the word cat, but now represented like that. You guys see that? Is this concept making sense so far?
So far.
Okay, so far, great. All right, so that's what we're doing. Well, as it turns out, BERT, let's say, has kind of a similar objective. But it's much more powerful. So what this means is, in the bag of words approach, as I said, you had vocab size, very big, very big, 50,000. Word to vec, you train on a data set. Oops, it should be much smaller. 256. BERT is kind of the same idea. It can also be 256, but but basically the argument is for the specific task. Now BERT, so I should say this. If you apply word to vec to 2.5 terabytes of data, and then you take that to any other problem, like using KNN, etc. This is state of the art, one of these algorithms. If you do the same, apply BERT, the general BERT, phase 1, to that data set, and you get vectors, the performance of BERT compared to word to vec will not be as good. So word to vec is still pretty good compared to BERT. However, if you apply BERT to a specific task, then for that specific task, the embeddings can be better than the generic word to vec embeddings. So for instance, what's going to happen with word to vec is that, let's take the word bank. Obviously, the word bank has multiple meanings, right? It has something to do with rivers, but it's also where money is stored, right? A good analogy is that with word to vec, it kind of just learns one embedding for bank, right? And that's it. With BERT, BERT looks at, whenever it's training, word2vec kind of just looks at the word and the co-occurrence of words. BERT will look at even multiple sense. So, you know, word2vec will look at, let's say, the bank is closed, right? And it kind of just looks at, you know, sort of like that. BERT looks at more. The bank is closed and the robbers broke in. Do you see that? Remember that when you feed the transformer, remember this, we were giving strings of sequences. The cat sleeps and then wakes and then wakes. So it's kind of looking at more context. So for a specific task, the attention mechanism will allow BERT to link these two words, bank and robbers, for instance, in a more strong sense. So whenever it sees this input, the encoding of bank will reflect money. Do you see that? Does that make sense? But if I give it the bank is slippery and eroded, that refers to a river. So when BERT looks at this sentence, it's going to create a vector for bank reflecting rivers. Whereas in the previous example, the bank vector, both of them of 256, let's say, reflects more, you know, banks. So do you guys understand the difference?
Yes.
Yeah. So that's the difference. So I want you to understand that at the end of the day, they're both creating vectors, right? No longer this gigantic vector. Now they create vectors, let's say of 256, but the features are a little bit more fixed in word2vec, whereas in BERT, they're a little bit more, they're better because when you give it inputs, now it knows how to pay attention to the words because it learned that, oh, when I see robbers and banks, they're talking about bank stuff. When I see, oh, I see bank and slippery and eroded. No, this has got a meaning of river. So every encoding of the word bank through the transformer, it's a little bit different given the context that it's seeing. And so the values here, let's say that feature X2 and feature X50, right? These are the semantic meaning. This one is more about dollars. This one is more about rivers, right? Just to give you an example. So here, for BERT, I think this is good intuition. For BERT, bank would have like a more 1.1, negative 0.1. You see that? Whereas this one, no, actually, did I do this wrong? I did this wrong, correct? If we want this to have a more river meaning, then this needs to be. Do you guys see that? Whereas here, for this representation of bank for another sentence, it said the bank and the robbers and everything. So obviously the context is more about money, bank stuff. So then this one should be like that. So the encodings change based on the context in a more meaningful way. There's more semantic because BERT has more understanding about what it's seeing, thanks to that attention mechanism and to the extremely large number of layers in the transformer. Whereas word tovec, first of all, it's a very small neural net and it doesn't have attention either. And so although they're both encoding at 256, BERT might have it. Now, keep in mind, though, as I said, for general things, word tovec is probably better. This is for task-specific encodings. So the taking out the vectors, the encodings from BERT don't exactly work really well for every problem, but they're good for that specific task that you trained it for. Any questions so far? No questions? All right, so that's kind of what I wanted to say as far as the this. I'm not seeing any questions. So let's go back then now to the book. So go to the book here. All right, here we are. So you should be seeing the book. Yep. All right, so let me make this a little bit bigger. All right, so I'm kind of motivating then. Embeddings, right? So I have some graphs here. Somewhere in here. I went too far. I'm really lost here. Oh, here we go. So, so semantic vector spaces, right? That's really what we're talking about here. So as you can see, kind of the story of word tovec starts with Nikolov et al. 2013, where it's using all these ideas, these vector space ideas, right? And you can see a vector space here. And so before like word tovec and all of this, this came from latent semantic analysis. You can take a read through that one. It's a nice one, you know, but basically the idea of like putting things in a space and then calculating distances here. So this example, I think, should show similar authors, I think, in this space, in this compressed space, I believe. All right, so anyway, if we look at word embeddings and neural nets, that's what I was talking about. Word embeddings look at the co-occurrence of terms in a document, but in a more simplistic way. Mikolov proposed new algorithms to calculate word embeddings, kind of how I described. One of the methods is word tovec. The vector space is based on the co-occurrence of the words. You specify a dimension specifically. The architecture just includes an input layer, an output layer, and a hidden layer. So it's not even a deep neural network. The input layer consists of the words and the vocabulary of size V. So you can see it's pretty big. They're one-hot encoded so that you can represent it. So remember, if we have the vector dog, cat, blue, right? For the word cat, we do 0, 1, 0. And this is for a vocabulary of just 3 words. Obviously, if you have 50,000 words, this is of size 50,000. So hopefully this makes sense. So the vocabulary defines the number of neurons in the input layer. These one-hot encoded vectors for the words in the vocabulary are the inputs to the input layer of the neural network. The outputs of the neural network are also the one-hot encoded word vectors, but this time using a softmax function. Similarly to logistic regression, the softmax is used to calculate a probability distribution over the word. So basically, in this case, the probability that word J in the vocabulary co-occurs with other words in the vocabulary itself. So here's a nice little graph. So basically in the training, this is the input. So notice it's a one-hot encoded vector of all the words in the vocabulary. So, we have cat as the word input. So this is a 1, the other ones are 0. We have a neural net of just one dimension. And then we have all the words again as the output, but this time the idea is that because we have a softmax, let's say we choose for 20 words, we do this on a 20 words that it's similar, 20 words that it's dissimilar. And the way to do that is easy. You take a window of the words that are closest to our word in question from the text, and then randomly we pick words that are not close to it, and those become examples of where it's not similar. So then what the algorithm should do is for the words that it's similar, it should give high probabilities, so high values here. And then for the words that it's not similar, it should give low or negative values, right? So you can see, for instance, the cat should have high probabilities for sleeps, for eats, meows, but the cat and the words space, ship, rocket fuel, should, black hole should not be linked. And that's how it learns. Does that concept make sense?
Yes.
Okay, perfect. So that's word embeddings. That's how the algorithm works. Obviously, this is not a transformer, right? But it's based on neural networks. There's no attention mechanism. And it's kind of just looking at what I described, whereas transformers provide more machinery to learn. It's got tons of layers, et cetera, and it's got the attention mechanism. So then that's word tovec, and then we end up with something like this. For every word, we have a vector of size, let's say, 256, where we have the values of it, and they look like this, basically. So for the word Xanax, which is a drug for depression, I think, and now we've got all the values of it, and that's it. And then these values can be plotted in a vector space. Okay, and then we can do inference because the vectors have meaning. If you want to learn more about word tovec, about how it works, I spent a lot of time writing this section 5.4. I explain every little line of code in word tovec, but that's outside of the scope of this semester, but feel free to read through it. Okay, then, so that's actually word embeddings for today. The next topic that I will just kind of quickly go through is auto-encoders, just because they're similar too. So that should be section 5.6. Yeah, 5.6, auto-encoders. So auto-encoders are a type, it's a similar idea. And if you notice, what's key here is that the word encoder. Now you have seen the word encoder before in the transformer, because if you remember, I said that the transformer has an encoder and a decoder, right? So it has an encoder and a decoder. So here's an encoder. So what are auto-encoders? Auto-encoders are, so although somebody might ask you, have you ever used an autoencoder? And then you would say, no, I've never used one. And then I ask you, have you ever used BERT? And then you say, yes, I have used BERT in my ethics homework. Then I would say, then you know what? You have used an encoder. All right, the only difference is BERT is a very complex encoder versus a plain vanilla encoder that you can build from scratch. Now you can learn everything that you want about simple autoencoders from this example. I'll just kind of quickly go through this. So autoencoders are a type of compression method where a neural network learns how to represent a vector of size m into a vector of size n, where m is much greater than n. So you're compressing it basically. Here, the input and the output vectors in the network are the original sample and the reproduced sample and the hidden layer of the network. Okay, so that's the architecture. So here, the input and output vectors are in the network are the original sample and the reproduced sample, and the hidden layer of the network is the new compressed representation of the input vector. The objective function minimizes the distance or difference between the original input sample and the reproduced output sample. So let's kind of think about this, because this is important for BERT to understand. Oops, there we go. So you should be seeing the whiteboard now. All right, so I'm gonna just finish this topic and then we'll do BERT in the second half, I guess, with the code. We should have time. All right, so an autoencoder, according to that definition, is this. So let's take an example that you guys know really well, MNIST. So the size of MNIST is 784. Size of here is 784. This is the input. This is the output. Do you guys understand that? But here, the hidden layer gives you full control, because you can say, you know what? I want this image to be reduced to size 100. This is the encoding, the neural net. Why does this work? Well, it's similar to word-to-vec. In word-to-vec, I just said that you give it words and the words associated with it, and it creates for each word, by the weights are basically the embedding. That's the same here. You know, I take an image that is 784 and I'm going to learn how to represent it as just this hidden layer of 100. Do you see that? I just do that. What's the advantage of this? The advantage of autoencoders is that, let's say that you're learning how to make an image similar to it, to reproduce the image, right? That's the idea. You give it this as input and you should get this image, something very similar, but running through the network. So that means that in the compression, it should get rid of data that it doesn't need, and it should just represent it with less neurons, okay, to get this output. So imagine that all the images are like this of cats. It goes through the neural net and you get same cat. You see that? Now, one key thing about this is, let's say that you train on a data set of cats, but then your autoencoder is built, and now instead of giving it a cat, you just give it a person. What do you think would happen if you run this image through this model? What do you think the output would be intuitively? Just tell me what you guys think. What do you guys think?
That it doesn't match.
Hmm?
That it doesn't match.
It's think of what it does. You give it a picture, it gives you a picture. What I'm asking you is, what would this picture look like, do you think? It's not a label like match or no match. It just creates that image. So what do you think that image will look like?
Cat?
Well, if you had given it a cat and then it runs, it gives you a cat. But now you're giving it this person, right? Running through a model that has learned how to reproduce cat images. So what do you think it'll do? Do you think it'll be a cat? Or do you think maybe it could be you made as a cat?
Okay, I see.
You see that? What is the name of this? It's very popular in the media.
Filters?
Nope. Well, filters, I guess, yes, but have you heard
Oh,
of this?
deep fakes. Yeah, yeah.
You guys have heard of this term?
Yeah.
You have, right? Deep fakes. Do you see how kind of this would work now with deep fakes? You build a model here, you give it the same image every time. Not, I mean, here and here, right? Obviously, it's going to be a corpus of millions of images. So it learns how to take any image and converts it into a, he filters it into being a cat. But if you gave it like a person, it might catify it, right? It might put whiskers on it or something like that. And so that's where the deep fakes, they're more complicated than this, but they kind of go from here. Does this make sense?
Yeah.
All right, great. So going back then to, so BERT, so I just want to connect this to BERT. BERT kind of works like this. BERT is an encoder too, with many more layers, right? Many more layers. The input and the output, just like with the encoder that we just saw, where it's the same, 764, or 784, is it right? 784, where it's cat, and cat, basically the same input, right? In BERT here, same thing. You give it the, but in NLP, the cat eats, the cat eats. Do you see that? Except that the goal of it is that this is, let's say, the label, if you want to think of it that way, and this is the predicted. The cat mask. So you give it the cat mask, and every time it's going to predict the word. Eats, for instance. It compares it to the original input, and which is the output. And so it's going to learn, it's going to train basically to learn the masks. That's why when you apply BERT to this problem, you're able to predict words correctly. But if you think about it, it's a similar formulation. The inputs are kind of the same, just like the inputs were kind of the same here, or with a slight variance and difference. Questions about this idea? This was an important thing I wanted to do, which is link these two concepts. No questions, guys? So anyway, so as I was saying, the input and output vectors in the network are the original sample and the reproduced sample. And the hidden layer of the network is the new compressed representation of the input vector. So what that means for our example of BERT is that possibly the last hidden layer of BERT is what? The embedding. Do you guys understand? Very much in the sense of like word tovec, and we had the embeddings. It's a similar idea. Not so good for generic tasks, but might be very good for specific tasks. The last hidden layer, because there's going to be, could be 300 layers here, or 1,000, or who knows. But the last one, but actually, This hidden layer may also be good, or one in the middle, right? So there's actually, I've seen papers where they've measured the performance of all of these at different stages, but they are basically embeddings of the input of the sentence, basically, as a generic way, if you want to think of it that way. Questions? No questions, really. Okay. So the objective function minimizes the difference distance between the original input sample and the reproduced sample. Usually the input and the output vector are the same vector in the autoencoder. However, denoising for images, for instance, in that case, you can think of the input vector X and the output vector Y as the same one, but with a little bit of noise, except that the vector X has noise. Therefore, this is more like Y is similar to X plus random noise, right? So it's got a little bit of noise. So that's kind of like what we're doing, because in BERT, you don't give it the exact same sentence, right? You give it the sentence and then the same sentence, but with one token replaced with a mask that it should learn. So that's the objective of the autoencoder. All right, so that was the other connection I wanted to make to encoders. I was hoping you guys would have more questions. I'm not seeing any questions here. But these are the building blocks that I wanted to discuss before getting into BERT itself, but we'll save that for the latter half of today. So let's go to, so now we should be ready. And you can read the rest of this chapter to understand about a little bit more about encoders. And then now the next section is this, right? So now we are back at the transformer. So we are back at transformers, and we're going to look at BERT in particular. So this is where I will start after we take a 10-minute break. So let me go ahead and stop sharing. I'm going to pause.